the last class in which new material will be covered. The only other class we might have then is on you. So if there's anyone who's at least considering doing the coding option for the final, then on Monday, class 7 will be devoted to discussing that and hints and so forth. So is there anyone who is at least considering the possibility? So now you wait and get out of this. Oh, but we don't have on well, anyone who's firmly committed to the oral sort of does not even go on Monday. Okay. So who might be coding? You. You might be, or okay. That's pretty good.
I'm leaning towards a oral option, but
okay.
I might show up.
Okay, all right. And we're gonna know where you stand.
I might show up anyways, in case you guys like to see.
And then okay. Okay, well, and much of what's going to be on the coding option, both we can do that. Well, that's what I covered last time on the treat method. Also, finite difference methods that we'll see today. So this is a problem we're still considering. Y double prime equals a function of x, y, and y prime on some interval a b with these two boundary conditions. So we saw how to solve that by treating it as an initial value problem for a system of two first order ODEs, but now taking a more direct approach. So the idea now is we set up a grid of capital N equally spaced points defined here between A and B. Since we have now all these N points are strictly in the interior, so this does not include boundary points. We define these x values with this spacing. Since we have N interior points, that means we're going to have N plus 1 subintervals that we're chopping into. So our goal is to compute the solution y of x at these x values, and so we'll call the solution values y1, y2 up to yn. So now what we do is we spatially discretize our ODE using finite difference formulas for derivatives. Here are the finite difference formulas that we're going to use. So in both cases, we use what's called a centered difference. So derivative, first and second derivatives at xi are approximated using function values at xi minus 1, xi plus 1. So we're using both left and right neighbors. Both of these formulas for the centered difference formulas are second order accurate. You see what we have here, these last terms on each line are the error formulas. And we see in both cases the error is proportional to h squared. One thing I want to mention, I think, where these formulas are given in the text, I think there's a typo I want to make you aware of. Okay. Yeah. So here are the same formulas in the text, but here it says y of xi. It should be x of I minus 1. It's correct here in the notes. Okay. So now what we do is where we have derivatives, so y prime and y double prime, we go ahead and replace those by these finite difference formulas. And so now we find this expression, LH of y is a vector that of values that comes from evaluating both sides of the ODE at xi, and we approximate derivatives at xi. But we rewrite the ODE so that everything's on one side, set equal to 0. So here we have, this is our approximation of y double prime, okay, minus f of xi, yi, and then where we had y prime, we replace at xi, replaced by our center difference for the first derivative. And we want y double prime minus f to be equal to 0. So now what we have here, this the system of equations, capital N equations, in the capital N unknowns, y1, y2, to yn. So instead of solving the ODE and its boundary conditions, and of course the boundary conditions, we're going to solve this system of N equations and N unknowns. Now, the questions at this point to where this system comes from. Really is about discretizing the derivatives. Okay. Now, these equations must hold for I equals 1 to n. But let's suppose I equals 1. So then over here we have y2 minus 2y1 plus y0 over h squared. And then here we have y for we have I equals 1, so y2 minus y0 over 2h. But y0 is not among our unknowns. We only have y1 to yn. But since x1 is the first interior point, which is just equal to a plus spacing h, x0 logically would just be a. So we're going to set x0 equal to a, which is what comes from this formula anyway, it's consistent. And xn plus 1 is equal to b. So then for convenience, we'll define y naught equal to alpha and yn plus 1 equal to beta. Those are our known boundary values of y at the endpoints a and b that come from the boundary conditions. So if we go back up here where I is equal to 1, we have y2 minus 2y1 plus y0, which is alpha. So we really would just fill in the value of alpha up here and also over here. Similarly, when I is equal to capital N, here we have yn plus 1, but that's just beta, so value of beta would be filled in. So the boundary values are filled in the system of equations wherever y naught and yn plus 1 appear. So it still really is a system of n equations and only n unknowns. Okay, so the challenge now is how to solve this system of equations, and also having some assurance that this really is a good approximation of the solution of the original problem. That as the number of grid points increases and as the spacing h goes to 0, that the computed solution really is converging to the exact solution. And that brings me to this next discussion about convergence analysis. So for convenience, I can define the vector x consists of all my interior x values. And I let y of x, so this function y of x, that represents the exact solution of a boundary value problem. So then I define, similar to what we have for type stepping for initial value problems, because for initial value problems, for convergence analysis, we had to show convergence, we first showed the method is consistent, then we showed it was stable, and then the two together showed that it's convergent. All of those same concepts apply here too. We just have to define them appropriately for the problem that we have. So local truncation error is still about substituting the exact solution into a numerical method. So that's what's happening here. So this notation y of a vector x means we're taking the exact solution and we're evaluating it at all the x values. So it's this whole vector. So basically it's a vectorized operation. So now we have this compact way of describing how we're substituting all the exact solution values into our numerical method. So, because y of x satisfies the original ODE, y double prime minus f equals 0. But because we're substituting in this approximation of that ODE, we're going to have something left over, and that's the local truncation error. So just like with initial value problems, we say that the method for this boundary value problem is consistent if the local truncation error goes to 0 as h goes to 0. And we lump an expression for local truncation error the same way as for initial value problems, substitute the exact solution into the numerical method that you have. I should mention that here I'm using these are real sensible choices to represent your derivatives. So you set different formulas that are fairly simple to evaluate and second order accurate. But if you use different formulas for the derivatives, then that would lead to different methods. So it wouldn't really be correct for me to say, this is the finite difference method for a 2-point boundary value problem. But it's the most logical choice for a finite difference. Okay, so as with initial value problems, to get a handle on what the local truncation error is, use Taylor expansion around xi, and that means taking multivariable Taylor expansions of f, multivariable Taylor expansion of f around xi and y of xi and y prime of xi. There's 3 arguments for Taylor expanding in three dimensions. Thanks. You also take into account that wherever you see y double prime in your Taylor expansion, that is equal to f, because y of x is the exact solution. So this is what you could do to show that, like for the method that I've shown you, the local truncation error is order h squared. So the method I've described is second order accurate. Now, more details about convergence analysis. Okay, so here are the definitions. I gave this definition already for local truncation error, what it means to be consistent. Now, for stability, here's our definition of stability. Now, it's a little cumbersome, but the main idea behind stability is the same as for initial value problems. That if you have that the difference between 2 solutions can be bounded in terms of the difference in the problem data. Like here we have, this is a difference in the boundary values. So the idea here is that a small change in the boundary conditions should not lead to a large change in the solution. And we're also assuming that the function f satisfies certain Lipschitz conditions in order for this to hold. So they're really bounding the difference between 2 solutions in terms of a problem data. And then for convergence, I mean, the same as for initial value problems, that the difference between the exact solution and the computed solution at every point goes to 0 as the number of grid points goes to infinity, as far as h goes to 0. It can be shown that the method I've shown you is consistent, it is stable, and therefore it is convergent. So we're going to look at linear and nonlinear problems separately because the approaches for solving the system of equations that I've defined is going to be very different in those cases. So if a boundary value problem is linear, then this is our linear second order ODE. I'm going to write it a little differently for convenience. So then I fill in the finite difference formulas for derivatives where we see them. and then multiply through by h squared, and we get this. And then, but notice throughout this left side of the equation, you have yi in a couple places, you have yi minus 1, in a couple places also you have yi plus 1. So we group by the group terms by the subscript of y. Now we have coefficient times yi minus 1 plus coefficient times yi plus coefficient times yi plus 1 equals this right-hand side. Now, when I is equal to 1 or to n, we have boundary conditions taken into account. So, for example, if I is equal to 1, this would be y0. So, we fill in the value of alpha, and then this whole term gets moved to the right side. That's exactly what happens in this case. Whereas if I is equal to capital N, here we have yn plus 1, that would be equal to beta. And this term would get moved to the right side. So here for I equals 1 and I equals n, we have equations with the boundary conditions taken into account. So those are now enforced. And then for all over values of I, from 2 up to n minus 1, we just have this equation as is. And what happens in this case is because each equation in the system involves only yi minus 1, and yi plus 1 for equation number I. The system of equations can be written in this form: matrix A times vector y equals vector r. So an A is a tridiagonal matrix. The vector r consists of these right-hand side values. Mostly it's minus h squared times values of r of x. But then the first and last equations, you have these boundary terms too. And it can be proven that if the coefficient q of x is non-negative, and if h is, the spacing h is sufficiently small relative to p, then A is going to be strictly row diagonally dominant, and also therefore guaranteed invertible. Now, the term strictly row diagonally dominant has come up before, chapter 5, for iterative methods, like for the exploration, that if A satisfies the condition, the Jacobi method is guaranteed inversion. By the way, the reason for rewriting the ODE so that the y double prime term is negative is, especially in the case if p and q are smaller 0, then the matrix in question is symmetric positive definite. And it's not an essential choice, but I want to play why it's not. Okay. Okay. I'm going to show you an example where we solve a linear problem. So here again, I'm using the matrix entries for the diagonal, the super diagonal, and the subdiagonal. And here are the elements of R with the boundary conditions taken into account in the vector R. So here's this example. Here we have a MATLAB code snippet that solves a sample boundary value problem. And the boundary value problem in this example is this problem right here that I used to illustrate the shooting method last time. So in this case, if we so in this case, p of x is equal to 2 and q of x is equal to -1, and then this function here, x e dx minus x, that's your r of x. So then we define all of these in our code section here. Okay, so here we define P, 2 equals 2, Q equals -1, and R of X is X e to the X minus X. We specify boundary conditions. Here we choose a small number of grid points, like last time we showed in method. This is a function, this is actually an exploration that to solve find differences. So you basically passing in a description of a problem of P, Q, and R functions, the boundary conditions, and number of grid points. This is the exact solution. So go ahead and so the function find a difference boundary value problem FTPDP returns a vector of x values and a vector of corresponding y values. So the approximate solution at those x's. So then we use this x and evaluate the exact solution formula at that x. So that way we can plot the exact solution and the computed solution. And this code snippet right here produces this plot of here. So here we have the exact computed solution. You can see they agree quite well. The error is shown over here. So yeah, there is some error. It's just too small to really detect from the plot over here. Okay, so questions about solving a linear boundary value problem by finite differences. Now, nonlinear case, much more interesting. So now we have a system of n nonlinear equations in n unknowns. So it's written this way: f of y equals 0, where f of y is a vector value function. So it takes the vector y as input, returns the vector f of y as output. It has these n component functions that depend on the vector y. And here are the component functions right here. So this middle one is for the interior. And you're all evaluating the interior as y, but the first and last one have to take a boundary conditions into account because you're using left and right neighbors of y value you're at. So that for the first one, we have y0 over here, which is alpha, and here. And for the last equation, we have y sub n plus 1, which is theta, here and here. So the goal now is to solve this system of nonlinear equations. And some time ago, in chapter 11, I discussed certain methods for doing that because we reviewed iterative methods for finding the root of a single nonlinear equation. So fixed point iteration, Newton method, CCAT method. And then how to apply a fixed point and the Newton's method and Gordon's method for solving a system of nonlinear equations. And those are methods that we want to look at here. So for instance, if you're doing the Newton's method, this is what Newton's method looks like, that your new y vector is equal to your previous y vector plus some step. And this step is described here. You're solving a system of equations. So really, Sk is equal to the Jacobian matrix inverse times minus f. Now this corresponds exactly to from Newton's method for a single equation. In that Newton's method, you have xk plus 1 equals xk minus f of xk divided by the derivative evaluated at that point. So instead of dividing by derivative, we're multiplying by an inverse matrix. That's what we're doing, accomplishing by solving this system of equations for Sk. Now, it takes some work to come up with a matrix, the Jacobian matrix of that represents the derivative. So the entries of this Jacobian matrix come from taking the partial derivatives of the component functions of f with respect to the components of y. Now, but because of how these component functions are defined, like the ith component of f depends only on components I minus 1, and I plus 1 of y. So that means that the Jacobian matrix of f is a tridiagonal matrix. And here we have the diagonal entries defined here, and then the superdiagonal entries, and the subdiagonal entries. Now, in the case of, for example, okay, yeah, we're like right here, for this superdiagonal entry, let's suppose that I is equal to 1. Then here we're going to have y0, and you would use alpha in that case. So for I equals 1 here, and I equals n here, you need to use these boundary values to fill in everything. Okay. Now, one of the problems I mentioned with Newton's method for system of equations is, as I've shown you here, you have to solve a system of equations every Newton iteration where your matrix is a Jacobian matrix. And for a general system of nonlinear equations, computing and then inverting that Jacobian matrix can be quite expensive. It's an order n cubed operation. How come Newton's method is a lot more practical for this problem, kind of problem, than for a general system of nonlinear equations? Yeah. So why is the derivative in this case really the Jacobian matrix so much nicer to work with this time? Because for general system nonlinear equations, you have to solve. Yeah, you are solving a system like this. It really is this system. General case, you're recurring 2/3 n cubed floating point operations for like Gaussian elimination on Jacobian matrix, or whatever method you're using. If you're lucky and Jacobian is symmetric positive definite, then okay, you're still incurring order n cubed operations in general case. Why not here? What's nicer about this case? And how expensive is solving a system when it's tridiagonal?
Is it n times?
Yeah, and PQ for where P and Q are the upper and lower bandwidth. But what are P and Q when it's tridiagonal?
1.
They're both equal to 1. So yeah, it's just order n. Yeah, so solving this system hardly takes any work at all, especially compared to the general case. So Newton's method, while it may not be so practical in general, and that's why we look at alternatives like Gordon's method, and there's other quasi-Newton methods out there that I haven't covered. See chapter 11. This here, using Newton's method as totally fine, is perfectly fine. We do need an initial guess. There are lots of choices here. Here's a very simple choice. Y for y0. It's just a linear function that goes from a line that connects points A alpha to B beta. So it's a linear function in X that satisfies boundary conditions. So you can kick off Newton's method that way. Here's an example. So here we have this nonlinear second order ODE on this interval from 1 to 2. I worked with this example last time for the shooting method. So then you compute your derivatives, y and fy prime. And now we have our system equations, f of y equals 0. And that's what we have in this case, where in this first equation, I filled in the left boundary value here and here. Here. And then for the last equation, I filled in the right boundary value with 1/3. Here and here. Oh, I see a typo. This f should not be here because I just filled in what f is. Right. I hope that mistake is not also in the book. Oh, it's not. Okay. Well, that's really. How did you hear that? Okay. And then from a Jacobian matrix, so using the formulas from above, the matrix has a fairly simple form. Okay, so we have, for the second derivative part, we just have an ordinary center difference. And then here we have a center difference for first derivative. And then that is, then we have derivative of f with respect to y filled in here. That's the 3y squared minus y prime. Okay. Right. Okay. Oh, then I have example here. Right here. So this, what this does is this evaluates f of y at any given x and y for some ODE. So here we have the we assume that the vector of x is coming in includes the boundary values. Also the vector of y also includes the boundary values. Okay, and then we also have our function f that comes from the ODE. That's passed to the function handle. So then we take the interior x, y values. So that's xi and yi are those vectors. And then we take this vector gives me y I plus 1, and then this vector gives me y so I minus 1. And those are convenience variables for evaluating the center difference approximation of y prime. So now I have x values, y values, and y prime values evaluated at the interior. So then I have, and then here I have my center difference approximation of the second derivative. So here I have f is equal to my approximate y double prime minus f of x, y, and my approximate y prime. So this is my function f for Newton's method. So I would call a function like this to evaluate this right-hand side to set up my solve. I still have to fill in the entries in the matrix. I have not shown you that. I think actually make that part of the coding final. Okay. Yeah, here are the formulas for Jacobian. Oh yeah, so I've left that as an exercise. Okay. Yeah, I think there's some explorations that are assigned for this section, but those are part of like homework 9. That since you can drop 2 homeworks, you probably know what's going to do it. Okay. Now, so I had a script from a previous section that solves this particular boundary value problem using shooting methods, or a function called shoot. But you can modify the code in that example to call find a difference not on your boundary value problem function implementation, and also plot the solutions in the same way. Oops. Okay, and you're certainly not limited to Newton's method for solving a system of nonlinear equations. 6-point iteration is an option. The secant method, as I've defined it for a single equation, that is not practical to generalize to system equations, but there are what are called quasi-Newton's method. Boyle's method is one of them that, in some sense, uses the secant approximation to improve the efficiency over Newton's method. So if you use a method other than Newton's method for solving the system, one advantage of that is you don't need the derivatives of the function little f with respect to y and y prime. And it actually is possible to prove that 6-point iteration applied to this system of equations does converge if the grid spacing H is sufficiently small. So think about how do you know fixed point integration converges? You need the derivative to be sufficiently small. Like for a single equation, you need absolute value g prime of x to be less than or equal to some, let's just constant capital L, that's less than 1. Or for systems, if you can show that like a norm of a Jacobian matrix is strictly less than or equal to some constant less than 1. So that's the idea in this case too, that you show that the Jacobian matrix for this for a fixed point equation that you're solving, like for your function g, is bounded in an appropriate sense to prove that it will converge. So that's the main idea for finite difference methods for solving boundary value problems that you discretize the derivatives to get a system of linear or nonlinear equations, depending on whether your ODE is linear or nonlinear. And then you use methods that we've covered fairly extensively to solve it. And then it can be proven under certain conditions that this works. That you get convergence to the exact solution. Okay. Yeah. Come to the end of the end. Okay, so we have questions about anything, including homework, final, whatever.
Yeah.
Okay.
Not in class related.
What?
It's not class related.
Oh, okay. Questions about ours? I know that was anybody? Okay, so I will be here on Monday for anyone who's interested in the coding option. And that for sure will be the last time we meet as a class. And then once you everything has to be in by May 9th. That's 3 weeks from tomorrow. So that's still a good amount of time. All right.